Hello and Happy New Year. I want to go ahead and start with a new PowerPoint for notes about electrons and light. Um, just to kind of review a little bit about where we started with light and color before the break. I know it's been a while, but if you can remember, we did the flame test, and there you saw that different elements will give off a characteristic color flame when they are lit. And then we also began to look at the emission spectra of certain elements. And the emission spectra, remember, was the colored lines that show up when you looked at the light given off from an element through the diffraction lenses, the little glasses that looked like 3D glasses. And so we're going to look at that a little bit further and basically answer the question here that's at the bottom of the page. How does the arrangement of electrons in the atom determine the color of light that it emits? Okay, first off, we need to do a little bit of a review just about light and color in general, perhaps some of the stuff you already know about light and energy. So I'll just go over this slide, and this is definitely something you want to get in your notes as well. First of all, the color of light emitted from an atom is based on the energy associated with the electrons. Light travels in waves packaged into bundles called photons. So think about that just a little bit. It kind of reminds me of like a firefly. Like you have a firefly that has this light kind of in its belly, so that would be like the photon. And then sometimes when you see it fly really fast, it looks like there's a trailing wave. That's kind of how I like to think about how light travels. But the little bundle is called a photon, and that photon travels in waves. And you probably remember about a wave, that a wave has certain characteristics about it. First of all, the amount of energy is determined by the frequency and the wavelength of the wave. The frequency is the number of cycles of each wave per second. And so if the wave has more energy, it's going to have a higher frequency. If the wave has less energy, it's going to have a lower frequency. The wavelength is the distance between the peaks or the troughs. Now, there's an inverse relationship between wavelength and frequency. When you have a very high frequency, that means the wavelength is going to be really short. So the shorter the wavelength, the higher the frequency. But vice versa is true as well. If you have a longer wavelength, that means there's a larger distance between the crest of each wave. If you have a longer wavelength, then your frequency is going to be lower because there's less waves moving past a point per second. And so also the longer wavelength is going to indicate less energy with the wave. Okay, so let's look a little bit more about this inverse relationship. Notice here that in the first axis, wavelength is measured in meters. Radio waves have a wavelength of 10 to the third or 1,000 meters. That's a really long wavelength. The picture of the wave in the box shows this long wavelength. Moving right on the axis, the wavelength shortens. Gamma rays have a wavelength of 10 times 12, 10 to the negative 12th. So this wavelength is very small. And the axis below the wave box, frequency is shown. Recall that frequency is the number of cycles of the wave per second. The frequency of a long wavelength is small compared to the frequency of a short wavelength. Think of it as if you're covering the same distance at the same speed, but one person is taking long monster steps and the other person is taking tiny baby steps. To cover the same distance in the same amount of time, the person taking baby steps, which would be the short wavelength, have to step faster, which would indicate the higher frequency. Also notice how wavelength and frequency are related to color. Red light has a longer wavelength but a lower frequency than violet light, which has the shortest wavelength and the highest frequency. Here's another look at the electromagnetic spectrum. Now, I do want you to notice that this electromagnetic spectrum is reversed. And I just want to draw this to your attention because it doesn't change how the spectrum is, it's just reversed. So I'm going to flip back to the last one we saw. You can see that the red end of the spectrum is on the left and the purple end is on the right. Well, on this one, it's reversed, and I don't know why, but sometimes they put it with the purple on the left, probably because it's got the smallest wavelength, and then as you read left to right, you go up to 700 or more nanometers for your wavelength. It doesn't matter which way as long as you're reading the axis correctly. And so I just wanted to point that out before we moved on. This is another thing just to keep in mind on the ACT is if you have a question that includes information about the electromagnetic spectrum, just make sure you kind of get yourself oriented along that axis, meaning, where is the short end of the wavelength and where is the long end, because the short end is always going to be your purple color and the long end is always going to be your red color. Okay, let's go ahead and get started with this one. Like I just said, the longer wavelengths are always going to be associated with red color, and the shorter wavelengths are always going to be associated with the purple color. So in this situation, you can see that the visible light part, you can see kind of cut out there. That's just a small part of the spectrum. Of course, you're familiar with the gamma rays. We studied that with the nuclear chemistry unit, and you can see that the wavelength for gamma rays is incredibly small, 10 times 10 to the negative 14th. Whereas at the other end, like we said earlier, you have much larger wavelengths at the red end. Let's see, where am I? I guess that's really all I need to say about this particular slide. Just making sure that you remember that the purple end of the spectrum has the shorter wavelength, but also the higher energy. Okay, remember those baby steps have to move faster. Okay, moving on. All right, so what does this have to do with chemistry and atoms? Well, if you remember from our study on the models of the atom, you learned that the Bohr model is used a lot in chemistry and science education, but it's really not the most up-to-date model. However, when we're talking about color and light, this model is actually really handy. So we're going to go ahead and use it because it'll make it easier for us to understand. So just to kind of review this model, notice that in the model the nucleus is in the center, and the rings or orbits around the nucleus, those are called energy levels. This is where the electrons live in the atom. Each energy level is defined by a number, starting with 1 closest to the nucleus and going out from there. See, n equals 1, n equals 2, and so on. Each energy level is defined by a specific allowable amount of energy. So what this means is that an electron in a certain energy level, it can only have a certain amount of energy that matches the energy level. And so that's going to be important when we start talking about the color that an atom will give off, because it can only give off a color that matches the wavelength that is generated by an electron in that energy level. Energy levels are different and unique for each element. The spectral lines in the emission spectra of an element shows the energy levels that are possible for each atom. So you can think of it as an orbit from the Bohr model matches each spectral line. For instance, since hydrogen only has 1 electron, it will have fewer spectral lines than an element that has many electrons. It's a little more complicated than that, but it works for now. So if you look at the spectral lines for hydrogen up there, we learned that there's really only 4. This particular picture shows a larger purple band that's kind of split into several different colors, but there's not as many spectral lines for hydrogen. because there's only one electron. And what this tells you, though, is that that one electron can be at multiple different energy levels, and it just depends on how much energy is given to the hydrogen atom. And then, of course, if you look at an element like neon, you see that there's a lot more spectral lines, and that tells you that there are a lot more energy levels that are associated with neon. Okay, so moving along. So how does the light come from the atom? So this is going to be a lot of information. So once again, you want to get this information down in your notes, and maybe even sketch a little picture, sort of like what you see on the screen there. So first I want to start with the little white circle, which is an electron. It's in the n=2 orbit. So go ahead and find that. At this point, the electron is in the ground state, or its home, if you want to call it that. In order for an atom to release energy as light, it first has to absorb the right amount of energy. This picture shows that the electron absorbs energy that would match a wavelength to produce red light, because you can see that little squiggle arrow going in towards the electron is red. When it absorbs the energy, it jumps up to a higher energy level. When it gets to this higher energy level, it is in an excited state. It instantly returns to the ground state, and in the process to returning to ground state, it has to release the energy that it has absorbed. Therefore, the light it releases is red. So whatever it absorbs, it has to release the exact same thing. Now look at the electron in the n=1 energy level. It's colored orange. This shows that a photon of purple light was emitted when it returned to its ground state. So what this tells us is that it had to have absorbed the same amount of energy to make it leap from n=1 to n=3. So here's a question for you. Why do you think the light emitted from the electron that falls from 3 to 2 would be red, while the one that falls from 3 to 1 be purple? So that's something I want you to be thinking about, and we're going to look at that a little more closely with our POGL. Okay, so I'm going to go ahead and stop for now. Be thinking about that. Why did that one electron, when it fell back down to its ground state, why did it release red? And why did the last one that fell from 3 to 1 release purple? Be thinking about that, and we'll talk soon. Okay, bye-bye.